Okay, thanks very much. Finance is sort of an interesting industry because it sort of doesn't tend to come up too much. It's not funded by the DOE or National Science Foundation or DARPA or anything else. So it's very underrepresented at supercomputing. And I'll just quickly plug that we're having a workshop on Friday all about supercomputing applications in finance, in algorithmic trading, high-frequency trading in London, it's sort of in investment banks. But it's actually a very interesting domain for high-performance computing, but it's a little bit difficult to get into, partially because there are a number of sort of barriers to entry, which a lot of banks have traditionally been very reluctant to essentially engage with academics and sort of share their code. So we really have the challenge here of trying to modernize their code. And what we're going to do in this talk is show how we're taking some of the key usage scenarios that are used in investment banking and how we're porting them, essentially how we're porting a library that's open source, which is a sort of representation of what a lot of investment banks do onto the Intel Xeon Phi. And some of the things I'm going to be talking about are very much in sort of a line with what you've heard already in either keynotes or in the Black Belt software development session if you were there at the previous session. But there's some very interesting sort of niche or specific problems that we're having in finance. And I think that's what makes this area so interesting. Like many industries, I guess the same is true of data science and machine learning. Financial engineers are really driving much of the computational work. It's a legal requirement for investment banks to measure their risk. This is a very computationally intensive process. And so there's unlike sort of data science and companies like Uber and LinkedIn and so forth, there's a lot more regulation in place in the banking industry. It's a lot more conservative, and with it comes a lot more constraints on innovation. So we're trying to innovate in a much more constrained environment. But there is a push towards ever more compute-intensive modeling, more robust modeling, increasing frequency as we move into high-frequency data sets. Those of you that have read Flash Boys would have read about the fiber optic link connecting New York and Chicago. There is an enormous amount of money and investment put into infrastructure, and I believe that it's one of Intel's biggest sources of revenue in this sector. And that's my understanding from reading the annual report. And the challenge we've got is that financial engineers often have a background in math and physics. In some sense, they're like many application scientists you see in other areas, except they're really not that interested in doing anything with parallel computing. You'll meet few financial engineers or what are called quants at a supercomputing conference. I happen to be one. I've had a lot of background working in investment banking and consulting for hedge funds. So it's sort of an interesting place to be when you sort of enter into supercomputing and almost no one is talking about finance, and I'm wondering why that is the case, because it's a huge industry. And I'm going to build on some research that was done in collaboration with Microsoft, Intel, and the UC Berkeley ParLab when it existed. It's now called Azure. The likes of Kirk Kutzer and Tim Matson and various others, Jim Demmel, were involved in some very exciting work, and I'm going to build on that work and apply it in the financial domain. And the title of this talk is a little bit misleading because I'm really talking about code modernization, taking legacy code. Don't have the luxury here of rewriting hundreds of thousands or millions of lines of code in, say, Julia or Scala or F#. And some people talk about this and fantasize about it, but nothing ever happens. And this work is guided by industry advisory boards. An industry advisory board, the work is, I gratefully like to acknowledge the support of Intel in funding this research. And we have an industry advisory board, including JP Morgan. And so some of this, a lot of the direction that we're taking is really from their advice. So as I said, we want to take some code which is inherently serial, and we want to parallelize it. That's the same problem that sort of everyone is facing with code modernization. There are some groups that were doing vectorization. We're using Craze and things like that long times ago, back in the 90s. But for the most part, most of the banks, most of the financial engineers, quants, don't have any background in parallel computing and wouldn't know sort of the difference between in-order execution or out-order execution, or what thread affinity is, and all that sort of thing. So what I'm going to talk about is research that's done in a business school, which is interesting. We collaborate closely with the math and the computer science department, but I'm actually in a business school, and I'm choosing a domain-specific approach to narrowing down the problem. So rather than a bottom-up approach where we try and think about, how to accelerate all these kernels, at an MKL, for example, accelerate various different kernels we need, I'm looking at this and saying, what does the finance industry actually need? And let's come up with a subset of problems that everyone is solving. And let's narrow the scope of the work and figure out essentially a good way to provide practitioners with guidance on how to port their code onto the Intel Xeon Phi, or how to get performance efficiency out of the Intel Xeon. So as I said before, much of this work is really coming from collaboration with Intel and UC Berkeley, and the sort of early works on sort of design patterns. I would say, being honest here, that some of that work has been criticized for being a little bit too academic and not practical enough. We all know about software design patterns if we've taken a software engineering course, but software design patterns say nothing about, of course, the mapping of the algorithm to the parallel architecture. And so one of the questions that we'd like to address is essentially, we now have a myriad of different architectures, and of course I'm excluding FPGAs, which are used a lot particularly in the high frequency trading by companies. We'd like to be able to write code, ideally that's portable, but first and foremost, we'd like to take advantage of the many core or multi-core architectures which Intel are providing. And we're sort of also mindful of the fact that we're moving towards Knight's Landing. And so, we don't really want to be doing offloading. Many of the considerations that are currently sort of bottlenecks or barriers for the Knight's Corner, we're trying to sort of be one step ahead, if you like, and think about the next generation of the Intel Xeon. So, as I said before, some people call this the ninja gap. It's a little bit more than that in the finance industry. You've got mathematicians who, if you talk to them, will just say, well, I'll rewrite your algorithm so it can scale well. In other words, they know enough about the math that they can rewrite the algorithm for you, and then they can find a better solution. So oftentimes the workflow is like a traditional workflow where someone who is a domain scientist writes some code and then someone just tries to optimize it. Oftentimes what you'll see is that the domain scientist, in this case the quant, has the ability to be able to choose a different algorithm which will scale. So this is a multidisciplinary exercise here between a systems architect or a systems engineer and an application programmer, in this case being a quant or a financial engineer. So as I said before, software design patterns very much caught up on the industry, are heavily used sort of programming approach is to use a lot of abstraction, to use a lot of these type of design patterns. And our pattern language was introduced by Kirk Kutzer and Tim Matson and others. And the idea is essentially, this was done across scientific domain, was to look at what are the core bottlenecks, the computational patterns. What are really, if you look at all these different applications in computational chemistry, physics, fluid dynamics, typically boils down to a number of core problems, core mathematical problems, or it's sparse linear algebra, dense linear algebra. And then we also see that there are different ways that we can architect the application. We can use, say, a model view controller, or we can use, say, a pipe and filter. And the idea is really essentially is to take a look at some of the most common applications, the most critical ones, the ones that have to be legally implemented under Basel III, which is a law for requiring banks to monitor their risk, and say, okay, how can we go about combining computational patterns with structural patterns and providing essentially a description of how someone with very little expertise in parallel computing can port the code efficiently. And I'll explain some of the challenges and why, in practice, that idea sounds great and rosy, but when you really get down into the weeds, it's nuanced. And I'm going to talk a little bit about this as work in progress. I should say the caveat here that although our goal is to create a sort of an Intel Xeon Phi version of this library, that is not available yet. So with a pattern-oriented approach, the idea is you define the scope of the software, You provide a common vocabulary for quants or application developers and efficiency programmers, and you try to essentially sort of encourage or enable modularity and comprehensive coverage of an application domain. And we provide essentially a language for a software architecture. And so, as I said, what we're going to do is look at targeting critical financial applications and showing how, in each of the cases, how we address those problems. And what we learned from it. Because it's not very helpful if you just hand over some optimized code to someone who's not literate in parallel computing. So one of the key challenges here is not just to throw it over the wall once it's optimized, but to enable someone to follow the steps in a somewhat systematic way. But there is somewhat of an art to this as much as a science, and that's the sort of the part that's difficult to articulate. So this is sort of the idea conceptually. We've broken down the financial industry or financial applications into a number of areas that we think are important, which tend to be very heavy, very compute-bound type of problems. On the left there, we see application patterns. We see a class of application patterns called derivative modeling. Derivatives tend to be very compute-intensive, and as we'll see in the corresponding examples, there are a lot of challenges in doing these calibrating these kind of models robustly. And there's a lot of need to do these calibrations more frequently, as I said, to higher frequency data. So we have application patterns. Some of them are familiar to people outside of finance, like grid-based PDE methods, like finite difference methods, sometimes even finite element methods. But some of it's very unique to the industry. Don't tend to see binomial trees as a technique being used much outside of finance. And then we have portfolio analytics, the type of analytics that investment firms will do. They're often trying to use statistical functions. So some of this overlaps with machine learning and doing some dimension reduction, a little bit like auto-encoding before you feed it into a deep neural network. There's dimension reduction there. It tends to be very compute-intensive model fitting to large amounts of data. And that's also compute, but it's also data intensive. And what we're going to do is we're going to take these applications and we're going to map them onto computational patterns. When I say map, I'm using that word very crudely, and we're going to identify really what is the crux of the method, what is the core bottleneck. And in my terminology, I'm using the word computational pattern, or in the terminology of Tim Mattson and Kurt Kutzer, it would be called a computational pattern. And then we're going to see, essentially, what opportunities there are for exploiting parallelism, not just within the kernel itself, or the computational pattern, but at a higher level. What are the sources of parallelism? Either task parallelism, data parallelism, it's a nested parallelism. And what we found is that most of the research in this area have got too stuck in the weeds, trying to speed up one particular kernel, and doing this sort of analysis as mathematicians, trying to find ever more efficient methods, when really you can stand back and say, well, actually, this application has a lot more layers of parallelism than you might, when you look at the problem from 10,000 feet. So that's what we do, essentially. And I'm not claiming that this is sort of a new idea, but I think that sometimes people get so caught up in trying to speed up one particular routine by a factor of 2x or something, when there's huge opportunities to exploit parallelism in the application. Okay, so we're going to look now at three examples of what are very common types of models in finance. And you'll notice that some of you might have heard the word Black-Scholes, and in fact in an earlier presentation that was given at the beginning of the session yesterday by Jason Sewell, he even showed some Black-Scholes code and how he sped that up by 1,000. So that was a financial problem. But in banking, they tend to use much more sophisticated models that capture sort of more complex behavior between financial instruments. And so really, one of the challenges is that the level of knowledge needed to understand these models is pretty high, and it's very different from other domains. Relies a lot more on sort of stochastics and randomization than in other fields. So we'll talk about calibrating these models, which is very important because these models don't work very well if you don't calibrate them properly. And if you don't calibrate them properly, they produce model errors. And model errors lead to loss of money. And banks don't like losing money when there's model errors. And we've seen some examples of that where models have produced completely the wrong results and banks have lost lots of money. So you can probably dollarize the impact of model error. And then we're going to look at the actual model itself, not just the calibration of the model itself, and look at some challenges there. And finally, I'll talk about some risk application, which is very compute intensive. It's called a Monte Carlo method, but it's a little bit more sort of exotic than what you may have seen before if you've done Monte Carlo in physics or seen those kind of applications elsewhere in other domains. All right, so calibration is just a least squared problem. That's the pseudocode. It's very simple. You have n number of options. So if you take Apple, for example, at any time, there's usually like 1,000 option contracts trading on Apple. And you typically screen out a lot of those because they're not really they're what's called illiquid, so they don't give you very good prices. And then you fit this model, which is where I have, as you can see there, price. That's the model. And then you compute the difference between the model and the observed price, which is the V hat. That's the observed price you get from the market. And then you calculate the root mean squared error. And the idea is that this sits inside an optimization routine. And you try to minimize, for a set of parameters, this least squared error. And I'm sort of simplifying things a little bit. It's a little bit more complicated than that, of course. But this is, for all intents and purposes, enough to get us started. And this is a little bit difficult to see, but what we did is we took Quantlib, which is this heavily templated language. It's several layers of abstraction, and that's just the way that people like to code in the finance industry. Lots of abstraction. C++ is really the dominant language. And we looked at how much time gets spent in the calibration, and we see that it's probably around 75% of the time, or upwards of 75% is spent in the calibration itself. And so we asked ourselves, okay, what can we do to essentially improve the performance? Given that if we just, we went back a slide, we had this, what we saw was, the fact that there was this for loop and we could exploit independence in that problem. So in Quantlib, as I said, it's heavily templated. It's full of several layers of abstraction. It's actually a real pain to work with, and that's often the way that quant libraries have been built, just to enforce a lot of modularity and take advantage of several layers of polymorphism and other object-oriented programming sort of tricks and design patterns. You'll see code sort of very much like this in C++. And there, right there, is that for loop that I showed you the pseudocode for, and that's what we're going to essentially parallelize and show that we can take advantage of this on the Intel Xeon Phi, how we can accelerate this code. So all this is, of course, is a reduction, and so this is one level of parallelism we can exploit. We have essentially a map and reduce. We have independent calculations of the calibration error at each step, and then what we can do is perform we can perform this using an OpenMP pragma statement. We can use this reduction operator. So that's fairly simple, but as I say in a moment, we'll run into some issues if we just sort of stop there. And so if we look at this on the host, and we consider just a Xeon with 8 cores, and we experiment with different thread of placing a number of threads, mapping them to the cores, number of threads to the cores. What we find is that as we increase the number of cores, we're getting some speed up there, and it's relatively close to, it's falling off from linear as you go up to 8. And also we're experimenting there with a number of threads per core. And we're seeing that in this case it's sort of optimal to have 4 threads per core out in this particular experiment. So we're able to speed up that code by probably a factor of 4. just using 8 cores. That's so nothing very exciting there yet. Now, if we look at the Intel Xeon Phi, we see that provided that we're able to vectorize, and I'll talk a little bit more at the moment, we're able to take advantage of vectorization within inside the calibration error function, and we're able to take advantage of some of the AVX short vector math library functions. We're able to essentially vectorize an inner for loop, which I didn't show you in that code. And in addition to the OpenMP, where we now have a loop where we loop over 1,024 options, n is 1,024, and then we allocate that to up to 60 cores. And we're getting very good speed up, and also if you have, what we're noticing is that it depends on the, if you map 4 threads per core, then you're getting reasonably good serial performance out of one core as well. But that's provided that you're taking advantage of vectorization. And we had to play around with the code quite a bit before we could vectorize and the actual model inside that. So there's an inner for loop, which I didn't show you. If you don't vectorize that, or if the compiler is unable to vectorize it, then of course the performance on just using one core is pretty poor on the Intel Xeon Phi. Of course, part of that is to do with the fact that it's running at lower frequency, it's different memory hierarchy, etc. But vectorization is a very important component to being able to get the scalability. So we're using a combination of OpenMP and then a vectorization with inside the error function. So we're getting a speed up here of around 30 for a calibration problem, just by using an Intel Xeon Phi. And what we're seeing is that if we just look at one utilization on one core, this problem still not generate enough work to keep the core busy enough. So there's still 25% of it idle. So there's opportunities there to somehow increase the workload or to somehow fully utilize the architecture. So we're still underutilizing, even though we're getting the speed up. So we're currently looking at how to sort of improve that. So that's calibration, and if we go back to this very simplistic diagram, which in some sense is sort of really just a reference point for as we sort of navigate through. I find sort of concept visualization to be helpful. So we've used MapReduce. We've actually used some vectorization and we've looked at a calibration problem, which is essentially a type of dynamic programming problem. And we've also, although I haven't highlighted it here, we've used a characteristic function inside the calibration, and that's the part that we vectorized. I'm going to say a little bit more about that now. So this is inside the function. That's inside the actual model itself is this pricing model. And one thing I love about this topic, and what keeps me really excited, is that the opportunity to change the algorithm for the architecture just opens up a whole new way of thinking, a whole new school of research. And techniques that work well in serial in computational math don't scale well on certain architectures. So one of the really interesting things is that you can solve these kind of problems using FFT, you can use quadrature, and this is probably true in any domain. You can use quadrature, you could use FFT, or you can be really smart and actually try to do what's called Fourier cosine expansion, which is even faster than FFT, because it faster mathematically, that is, it converges faster. And then we can see here, just on the left, that's the error, and then on the right, that's the number of collocation points you need, or quadrature points. And what we're seeing is that if you can use some clever tricks, you can get much faster convergence and reduce the error of with much less work. But the real question is what is the computational cost in relation to the number of collocation points, n, or the number of quadrature points? And again, that's something we're currently investigating. And it may turn out that what worked well in serial doesn't work so well on an Intel Xeon Phi. It may turn out that the algorithm, or the best method for solving the integral on the Intel Xeon Phi is not the same for the Intel Xeon. And so just because of parallel scalability properties of the algorithm. So we're mathematicians, so we're able to sort of open up the black box and play around with it. And it's a lot of fun to be able to sort of completely sort of change the entire stack, if you like, have complete ownership of the stack, and decide to sort of dip down and choose a different method because it scales much better. And I believe that that's done in other domains as well. I've seen machine learning people picking certain types of stochastic gradient descent methods because they scale better, and that's become very favorable within machine learning. And it's a similar kind of idea here as well. And so if we profile the code and we use a quadrature method, if you fit something like Laguerre polynomials, I don't know if you're familiar with polynomial or basis functions, but if you fit Laguerre polynomials, what it becomes the rate determining step is a QR decomposition. And so while this method is favored and mathematicians like it, it's not the best choice of algorithm really to scale. QR decomposition does not scale well, and we're seeing that around something like 96% of the time is being spent in that QR decomposition. That it is essentially this eigen decomposition, just to find an orthogonal basis for Laguerre polynomials. And these matrices aren't very big either, so we've got the problem where for each option you need to solve it using a pricing model, but the matrices aren't very big. It's not worth deploying that on an Intel Xeon Phi. However, if we took 1,000 options or we took 60 options and then we solved a QR decomposition on every single core and we were able to vectorize parts of the QR decomposition, that's an interesting problem. So we're thinking about right now, should we do QR decomposition or should we do FFT? With an FFT on every core and try to take advantage of any vectorization. Should we do all the options at the same time? Or should we just do a very, in other words, what often governs the mapping of the algorithm, the architecture, is what resolution is required in the algorithm. That determines the workload. What tolerance there is for stability of the algorithm, that's often determined by the application user. Some banks want only the most robust algorithm there is, and they will not accept anything less. And it has to be mathematically rigorously proven to converge under all possible scenarios. Other people are willing to take shortcuts and say, you know what, we can assume that we'll just use 2 Laguerre polynomial functions. That'll be enough for us, and we'll cut corners. And hey, in that case, we know a closed form solution for QR decomposition. We don't even need to do the QR decomposition. So there is this trade-off between performance and stability of the algorithm, which rears its ugly head again. So that's this profiling of one type of stochastic volatility model called the Heston model. And again, we see, if you look down even further, we see some overhead provided by these sort of overloaded operators, which there's not very much you can do about that. That's part of the pain you have for sort of C++ templated programming. And using polymorphism. And so that's really the problem that we have, is coming up with essentially techniques and we use different models. We see the same thing again. Finally, we picked another model, and there's at least 10 of these different models that are used, and under different regimes, they make more sense to use. And we see that we take out this sort of linear interpolation. Hopefully you can read this on the right-hand side under called functions. The rest of it is spent in transform. And we're actually working on taking out this linear interpolation. We don't need it. And then the rest of the time is spent in the transform, which is the fast Fourier transform. So again, the opportunity to maybe compare using a fast Fourier transform with, say, using a quadrature method, maybe a Simpson's rule, something much simpler. Is it robust enough? Does it scale better? So while we started out with design patterns, we find ourselves going back into, but hang on a minute, you can swap and change the bottlenecks as well. Which one is best? And so what we're trying to do is come up with essentially a set of rules or guidance on what we think are the best choices of algorithms and sort of the pros and cons of robustness versus performance versus essentially, scalability. That comes under the category of performance. And also, I guess, convergence rate, because that determines the amount of work that each algorithm is generating. So a lot of this sort of gets into the drudgery of MKL, and we'd hoped originally that we could just throw everything at MKL and just pray and hope that worked. And our thinking is shifting to MKL is an excellent resource, but there are algorithms out there that we found we might want to consider using, and we're working with the MKL team to let them know about this. And so that's exactly what we found with this example. So this is the final example. This is with risk. This is how do you simulate how much money a bank can lose in one day. And they're very concerned about this because they have to have enough capital in place against the 1 in 120 negative event that happens. As we saw in 2008, things didn't go too well for the financial sector. And so a lot has changed since then. And they're running these very compute-intensive Monte Carlo engines now for all these different options. And things get tricky when the options have some sort of complexity to them. And in finance, these things get more and more complex, and that's because when things are very complex, less people understand them, and you tend to find more opportunities for arbitrage and make money out of them. And so it's an interesting game. But what we're using here is a technique called, this is how you set it up in Quantlib. This is how you specify essentially the method. We're using antithetic sampling, which is a type of symmetry-based sampling to reduce the variance. So that's a sort of technique in numerical analysis which reduces the workload. We're using, we're setting up essentially the code so it mirrors what's now become an industry benchmark. You may have heard of STAC, the Securities Technology Adoption Council. I think that's the right name for the acronym. But they are providing a set of standards and benchmarks for different architectures, and this is one of them. Now, all the implementations so far have just been raw C99 code, without having to worry about all this templating, abstraction, and the sort of the real world, sort of vagaries of software libraries and analytics libraries, which have to cater to many different parameters and usage scenarios. So, in a sense, what we're doing here is we're trying to get to a stage where you can benchmark a real-world analytics library and use that as an example of a more realistic benchmark than just some raw C code that someone puts some pragma and rolls in and everything else and done all the tricks. That may not necessarily be the best way to learn how to, for a quant or financial engineer, how to optimize these libraries. And so, we set up the parameters here. The samples there is the number of paths, and that sort of generates the workload. And if we run that through the profiler, what we see is that around 50% of the time is spent in this least linear squares algorithm. If we dig down further, we'll see that that's actually using singular value decomposition. A problem which rears its ugly head in many applications, in image recognition, in data analysis, and SVD does not scale well in parallel. It's one of those problems which that many people have looked at, and it's a little bit like using preconditioners for solving linear systems. It's the Achilles heel of parallel computing and computational math. So we're stuck here. When I say stuck, we've landed on a kernel which doesn't scale very well. I'll show you that in a minute. And we're trying right now to figure out a clever way of avoiding using that kernel entirely while still guaranteeing robustness. And we're also talking to the MKL team to see if they can help us with this particular problem. So that's profiling of code, looking at different examples, looking at a real-world library that is sort of somewhat typical of what banks would use. Of course, getting access to bank code is like, is probably easier to do, but is probably easier than than robbing the bank. It's very difficult to get hold of a bank's code, and so we have to work with sort of a representative example. Random number generation is really the main crux of this approach. There's two steps, essentially generating random numbers and then solving this linear least squares problem. And if you use the MKL random number generator, what we found is that this setup stage doesn't scale well on the Intel Xeon, the Intel Xeon Phi. You end up having to copy streams across for each number of threads. And it's very important you preserve certain properties of the random number generator, mathematical properties, otherwise it doesn't pass certain tests. So we're using sort of the MKL sort of best of breed product here for the random number generator, and then what we're finding is that the setup, that's the blue line there, this is on the host on the Intel Xeon, does not scale well. In fact, as you increase the number of threads, the performance is going down because of the overhead. So the generation part scales nicely, almost linear, but it's the setup. And we've not found a way yet to, and we've spoken to some people at MKL, but we've not found a way of dealing with that overhead, of setting up the stream, the parallel streams. And the story is, somewhat similar on the Phi. We're able to get, if you just take the generation step, we're able to get around, sort of a 20x speed up just for the generation, but it's the setup which is sort of taking up too much time. So what we did is we sort of played around in the literature a little bit, and we came up with, we found a different type of random number generator which scaled much better. It was developed by two Japanese mathematicians, Matsumoto and Nishimura, and that is a type of algorithm that scales much better, generates random numbers of all the right sort of properties, passes all these sort of battery tests, and it scales better. So this is an example where we had the luxury of a little bit of domain knowledge and said, okay, we'd love to use MKL, but it's not scaling properly. Let's try something else. So, who knows? Maybe this ends up in MKL one day. We don't know. So this is somewhat interesting because then, as I mentioned before, that's the parallel random number part, and then we've got the issue of the SVD. And the SVD, as I said, does not scale well, and that's one of the problems that we're really struggling with is, can we somehow avoid this step? Can we rewrite the problem? Because SVD is the only technique which will guarantee solution of a linear least squares problem. And linear least squares problems arise a lot in statistics, computational statistics, not just here in calibration, but pretty much in weather simulation and computational physics, where you're fitting models to observe data, satellite data, that kind of thing. So what I'm saying here is very sort of spreads to many other industry verticals. And again, we're seeing this, sort of atrocious speed up of the SVD compared to the number of cores. So our task right now is to figure out, what we do here. Do we take some shortcuts and pray and give up a little of the robustness for performance? We can easily do that. In fact, that's what some people are doing. Or can we hold ourselves to the highest possible standard of numerical robustness and get performance scalability as well? And that's a trade-off that we're sort of battling with. Again, we sort of started out with this sort of rosy, idealistic view that we could approach everything with sort of parallel design patterns, and we think that gets you some of the way there. It's a very good way of conceptualizing how to go from legacy serial code to sort of modern parallel code. But there are tasks for us here in the supercomputing community, and particularly those of you that are interested in computational math, scientific computing, MKL, etc. There are some problems which the financial domain is throwing back to us that may be arising in other domains too, that are worthy of seeking attention. So I hope that for those of you that sort of came in here for this talk because maybe you're interested in finance, but you're mainly in the supercomputing industry and in another field, you'll see that there are enormous opportunities here to get involved with some very groundbreaking work where there's very little pre-competitive research. Because as I said, no one's funding this sort of research, none of the government bodies, and banks tend to be a little bit lazy about sort of staying on the pulse when it comes to modern algorithms for these kind of architectures. So in summary then, we've profiled Quantlib, which is the sort of the best open source financial library there is. It's a beast of a library by my standards, and I've worked with quite a few libraries and banks. We've identified a map-reduce pattern to take advantage of higher level parallelism in the model. And then we've combined that with vectorization. I didn't mention that we actually use a lot of complex arithmetic inside the volatility models. We've taken advantage of some of the short vector math library AVX instruction set to get the vectorization. And we'd also essentially sort of played around with different thread infinities and thread placements. And what we found essentially are that we've hit some bottlenecks, and that we really need to sort of figure out, how to approach it, either as sort of parallel computing optimization experts, or maybe trying to reformulate the algorithm a little bit so that it will scale better. But overall, we think that this is a great approach for, in general, for setting a sort of the dialogue and getting everyone on the same page. And I've been coming to supercomputing since 2003. I think my first one was at Phoenix. You'll be amazed at how behind the times people are in the finance industry, still running things on serial computers. And so there's a huge gap. And I think that it's a very exciting place to be right now in terms of having a high impact by writing code and demonstrating the financial practitioners how to take advantage of vectorization and OpenMP, and also what kind of algorithms scale well for some of the most common usage patterns that we see in risk and derivatives trading. So that concludes my talk. So thank you very much for your time.